You are welcome back to the last day of this course. So I want to appreciate you for coming since Monday. You were here Monday, Tuesday, Wednesday, and today. Today is the last day, and we are going to discuss some other aspect of some other analytical aspect of Ricci flow. Okay, or let me say analytical tool for studying Ricci flow, another aspect of it. So we will discuss about differential Harnack inequality and some entropy functionals, which enable us to see Ricci flow as a gradient flow. Okay, so the plan of the lecture for today is as follows. Let's we'll first look at what we discussed yesterday, just briefly. Then we'll start today's business. Okay, in last lecture, we talked about a maximum principle, and we see maximum principle for scalar function. Okay, then we'll see weak maximum principle, and then we can apply this to nonlinear reaction diffusion equation. Then we saw Hamilton matrix maximum principle. Okay. Then we also discussed about the curvature derivative estimates, how to get an estimate on the higher derivative of curvature operator, a curvature tensor. Then we saw BBS estimates yesterday. Then we briefly talk about curvature blows up at finite time, that is singularity, at finite time singularity. So we discussed this yesterday. So today we want to start with differential Harnack inequality. Differential Harnack inequalities are a very important tool, yeah, which allows to study Ricci flow. Okay, we want to look at it in an analytical way. So this is very, very important. In the first paper of Perelman in 2002, he presented this new kind of Harnack inequality, which involves both the adjoint linear head equation and Ricci flow. Okay, this led to the complete new approach to Ricci flow, which allowed the interpretation of Ricci flow as a gradient flow, which maximizes different entropy functionals. So the main goal here today is just to explain this analytic tool. Well, in full detail, put that way, for the two examples of heat equation and Ricci flow. We will start with a Li-Yau result, with its original result on linear heat equation. Then we will discuss Hamilton's matrix Harnack inequalities for heat equation. Then we discuss it for the Ricci flow, and we will end with Perelman's entropy formulas. Okay. Li and Yau, in their paper, their seminar paper in 1986, okay, they presented the pointwise gradient estimate, which is now known as a Li-Yau Differential Harnack inequality. And this inequality is a gradient estimate, okay, on the positive solution of linear heat equation. It's called classical Harnack inequality because you can integrate it along a smooth path, and then you get a classical Harnack inequality. So then after that, Hamilton later proved a matrix version of Li-Yau, okay, under some slight different assumptions, and that is known as Hamilton Li-Yau Harnack inequality or Harnack estimate. So this also is was extended to the case of Ricci flow, and we'll discuss all those today. Okay. So let's start with Li-Yau Harnack inequality, okay? And we'll give this with respect to linear heat equation. Okay, this is the statement of the theorem. That's right. We start with M, okay, being compact Riemannian manifold. So in this case, we take a compact with without boundary, or with if there's boundary, we say the boundary is empty. Originally, in the paper of Li-Yau, it is on a with a boundary, and they impose some convexity condition on the boundary, where the Neyman the boundary condition is imposed together with the heat equation. But in this case, we just have M compact, and the condition on M is that the Ricci curvature of M is non-negative. So then if you now have a smooth positive solution to the heat equation, okay, let's put this way. We have introduced this object that is a Laplace Perelman operator, okay, equals to this. If this is equal to 0, where U is function here, okay, X in M and T, well, in this case, now let's just restrict T to this interval, okay. Now, so their result says, if you have this, then this solution, solution U satisfies this inequality. Okay, this here means partial U, partial T. Okay, that's the meaning. So in that case, it says UT U minus. Let's write well. Get rid of U square over U square plus N over 2T is greater or equal to 0. N is the dimension of the manifold. So this is a gradient estimate, and it is the one called Li-Yau Harnack inequality. Okay, because if you integrate this along a path, which I'm going to mention, you will get classical Harnack inequality, where you can compare solution, okay, to solution at different time. So that is a classical Harnack inequality. So this one can be integrated along a smooth path on the manifold. So you pick a 2 point on the manifold, then you can find a path between the two of them. Okay, then you can integrate along that path. Then if you use that, you get a Harnack inequality. We are going to do that. Then let me just move on. Okay, this is the Harnack inequality when this is differentiated. I mean, when this one is integrated along the path. This equation in red is what we have. Let's write it down because we'll mention it. So U x2 C1, put this way. So after this, the corollary from this gradient estimates is the gradient estimate. The corollary is this classical which is Ux2, okay, T2 is greater or equals to Ux1, T1 with a T2, T1 to the power of minus n over 2, and then you have E, the power of what I call L here. Let me say the L now is with respect to X1, X2, T1, T2. Let me just put this way. So where this L, minus is here, this exponential, this L is defined as this quantity, okay, infimum of 1/4 of this integral. And you see this gamma dot here. With this, we'll define it, okay, as a curve. Now, in our, I think in the first lecture, giving the background of differential geometry, we said we define a curve this way. I think we say if you have a curve, there we say a piecewise smooth curve. So let's say we have a curve, in this case now, a smooth curve from this interval to R. Okay, we define this. Maybe in this case now, such that this is 0 is x1, and this gamma 1 is x2. Some this nature, we'll define this. And from there, we now said the distance. Okay, let me say this. This interval, let's say this is interval is 0, 1. And this is our manifold. Then this gamma is a function that defines 2 points here. Gamma of 0 at this point, which is x1, gamma of 1 at another point here. So this case can be joined together with a smooth path. You can move from here to here. And then you can have as many parts, you know, that join the two places. And we mentioned that the distance between these 2 points is taken as the infimum of all this smooth curve, the infimum. So we define the distance of this curve on this on manifold now, the distance of the curve. We define it as a L, okay, of gamma as the infimum of this integral. I think we give something like this, where we respect to the metric of the manifold, G. So we define it as this. To the power of half, which is the same as just say over M with respect to dt, which is the same as a infimum, this integral, okay, dt. So this infimum is the length of the curve, okay, and the gamma there is that curve. So the integral in this bracket is the length of this curve gamma. So this is a Differential Harnack inequality, okay, of a Li-Yau and type. And let's quickly, we will try to do the proof, okay, just summarize the standard result, which has application. In fact, in partial differential equation, in geometric analysis, this theorem is very, very important and is used very fastly in the study, in the theory of Ricci flow. So we will go through it. But before then, let's quickly make some comments. Okay. So let's make some comment before we prove that. Okay. If you have this is curve. The infimum of this is the length. So if we are on a geodesic, let me put this one here. Remark. So if we are if M is a geodesic manifold, if M is a geodesic manifold, okay, this L, the L here that we have can be expressed explicitly. Put 1 T2, okay, I'll put a semicolon here, as d square distance x1, x2. So if we recall, in one of the lectures, we said this curve help us to get the distance on this. If you say this is a P and this is point Q, okay, we define the distance with respect to the metric PQ, the one we use to make our manifold a metric space, and we use that. So that is the D here you are now have here. So this is now geodesic distance. Okay, geodesic distance can be taken as the infimum of the path between these 2 points, which is called geodesic. So this L in this case will be D square. Okay, we have 1/4T2. So this is taken as a 4T2 minus T1. So you have this if it's a geodesic curve. And another example that we should be familiar with is suppose our manifold is a flat Euclidean metric, Rn. Let's see how we write how L is written in that sense. If we are on the Euclidean, okay, Rn. How do we write L? L is just a straight line. If it is not a curved space, like in this place, this is a manifold. Okay, like you have a sphere. If you like, let's say you have a sphere. If you take 2 points here, another point on the sphere, another point on here, the paths from this point P to this point Q is not a straight line, except you want to punch through your sphere. So it's going to be something of this nature. You want to move like this. That is how you can move from P to Q. But if you're on a flat space Euclidean, this time between another one point P to Q is just a straight line. Okay, so in that case, this gamma we have here, okay, will be taken is taken as distance between x2 minus x1. So that is just the, if this is point that is P minus Q, that's just the line. So you have that to the power of 2. So in that case, L will be written, okay, L of x1, x2, T1, T2 will be written as this x2, x1 square over 4 T2 minus T1. So you have that. Okay, so that is in the case of Rn, if you take fundamental solution of each equation, okay, which we call the Euclidean heat kernel, okay, Euclidean parabolic heat kernel, which is given this way, hxt, which is 4 pi t minus raised to the power of minus n over 2 to the e minus this absolute value of this vector x in Rn square to the power, of over 4 over t. So this is the fundamental heat kernel. So you have this as the fundamental solution of each equation. Then the inequality of this Li and Yau becomes equality on this. Okay, if you put this instead of u, because this is the fundamental solution of each equation on Rn, if you put there, then it becomes inequality. And that's why we say this inequality is optimal. Okay, so Li-Yau inequality is optimal. That inequality is optimal inequality. Okay. As well, we can have a version of this on manifold, but instead of this norm of the vector here, which serves as distance, you just have distance, geodesic distance. So you have geodesic distance, just like what we wrote there. Instead of this guy, if it is a manifold, okay, you just have, instead of this guy, you just have E minus this square of x1, x2 over 4 t2 minus t1. So that is a comment that we just need to make here. Okay, now we want to prove the inequality that we have there, that we have on the board, okay? And to prove that inequality, well, to make life simple, let's prove a lemma, which is a fundamental lemma. We just apply that lemma, is computational. We just compute and we'll see. And the lemma is given here. Okay. Suppose you have a Riemannian manifold, okay, with Ricci curvature greater or equal to minus k g. Okay, this is Riemannian metric. The product of this k minus k and g. K is strictly greater or equal to 0. So suppose we have a smooth function f. At least f should be C2 here because of the Laplacian. So a smooth function, at least C2, in x is a smooth, which this f depends on x and t. Okay, but it must be at least C1 in t and C2 in x argument. So you have, we are given this equation. If f satisfies this equation, and we have a quantity f, we call this Harnack inequality because from this quantity, Harnack inequality can be built. So from this Harnack quantity, okay, this capital F will, if f satisfies this equation, okay, then this capital F defined as this satisfies this evolution equation that we have here. Satisfy this evolution equation. So that is a lemma, and we can easily compute that. Okay, let's okay, let's see. To make life simple, if we want to prove this, okay. Okay. Yeah. Let's say f is given as t of f squared minus derivative of f with respect to t. So this is f. Then we want to show that it satisfies this equation. Now okay, let's use this formula so that it will not, it will be easier for us. Let's use, there's a formula called Poincare. It's called Poincare Linkowitz formula. Well, let me just call it Poincare formula. Yeah, on Riemannian manifold, it says that if you have a smooth function, let's say C infinity function on M, it satisfies equation of this nature. The Laplacian of this is 2 Asian of f squared plus 2, this is the inner product of gradient of f and gradient of Laplacian of f, then plus 2 Ricci multiplied by gradient of f, gradient of f. So we can start with this formula. And again, there's something we know here. If you apply Cauchy-Schwarz inequality, can easily see that Asian of a function is greater than 1 over n of Laplacian of f squared. So this is a simple computation from Cauchy-Schwarz inequality. You have this. And if you put this one here, you have, if you substitute this here, then you have this is greater or equals to 2 over n f squared, then plus 2 inner product of this from that formula, then plus 2 which is of gradient of f, gradient of f. So you have this. And from here, this is what we want to do. We want to prove this we want to prove this evolution. So the idea is that I want to have this f. I want to compute Laplacian of f and possibly compute the derivative with respect to time of f. Then you subtract and you find out this right-hand side. And that's what I'm trying to do here. The reason to do this is that if I want to compute Laplacian of f, then I will have Laplacian of norm distance of gradient of f here. Okay. And that is why I'm doing this. So with this, I can now compute Laplacian of f. Okay, which is Laplacian of, let me just put t of gradient of f squared minus derivative of f. I can compute that. So this is just t. So this Laplacian is a space dependent derivative, not time dependent. Meanwhile, what we are doing here is on static manifold. So our metric is not Ricci flow. Okay, so Ricci flow is not coming to place here. We are discussing original result of Li and Yau. It's on linear heat equation, not on the Ricci flow. So this is not dependent on t. So I can take that t out. Then Laplacian on this f squared, then minus Laplacian of this. I take this out. Laplacian on f. So, and then from here, sorry, this is just f. Yeah, okay, I'm correct. So you have this. So from here, we have this from here, which we can substitute. And this. Then if you look at from here, okay, if f is this, and the given equation is okay, this is the given equation. From here, we can see that our Laplacian of this is minus f over t. Okay. If you could do that, and you can substitute that here, because this one is coming in here. So you can substitute that here, you substitute that here, we substitute that in. Okay, let's write so that we'll see it. This is not greater or equals to t. We are substituting this here. That is 2t per n. Yeah. Then plus this one is 2t minus. So here, what next? We have the value of this. We just substitute here minus f over t here. Here we have minus f over t. Here we have minus f over t. Substituting that, and then you will have this together with the condition that this will be of this one will be greater or equal to minus 2k. Oh, sorry, t is here, t is here. This one has t. Then this one is 2k. Because Ricci itself, Ricci curvature is greater or equal to minus kg. So this guy is a Ricci of grade f and f. Maybe I will write neatly because of people with a small screen. Let's write the whole thing. You have the condition from a dilemma that Ricci is greater or equal to minus kg. So by this, Ricci of f grade f will be greater or equal to minus k g that f at f. So this is the inner products of this and this, which give us minus k gradient of f square. And the t you have there. So with that, we have Laplacian of f is greater or equal to 2t over n. We substitute minus f. Okay, so this is going to be minus f over t squared. Then the next one is going to be 2t product of gradient of f, gradient of minus f over t. Then the next one is just this, minus 2kt of f squared. And the last term is no, it's plus here, minus f over t. So you have substituted that. And doing that, you will arrive at what you have here, what we have there, what we have there. You can look at this one. The first term will come out from here. You have the first term on the left-hand side. Let me just write. From here, you have the first term there, because this is minus. You take that minus out, that is minus 2. Okay. Gradient is just gradient of f over t. T is here. So you have gradient of this f, gradient of capital F. That's what you have. That's the first term you have there. Then the second term, you have this, minus 2kt gradient of f squared. So from this one, gives you the third term. This is f squared. Okay. This is, when you square it, it becomes plus. Then t squared, t will cancel this. So this one gives you plus 2 over n t f squared. Then from here, if you this one is time dependent and this is time dependent, you can just use quotient rule. And then when you do that, what do we have? So keep this one constant, differentiate this. That is going to be minus derivative of f. Okay, y t is kept constant. Then you keep this constant, you differentiate this. Then that term will come out, and you have this plus partial of f. Then you have minus f over t. And then when you take this one to this side, it becomes this f minus this f greater or equal to the rest term you have there. So with this one coming here. So that is what we wanted to prove there. Okay. Then having done that, we can now go ahead and use that to prove the theorem. Okay. This is we have established this lemma. We can now prove the theorem. And what is the theorem to be proved? Here is the theorem that I wanted to prove. Is still, yes, I still have it on the board. Okay. So let me remove this so that we can quickly discuss that. Okay, I want to leave that. Can remove this. Okay. Now, to do this proof, let's quickly notice some things. If from the heat equation, it's still on the board, from the heat equation, if you take f to be logarithm of u, let me use log so that we write it very well. This is a natural logarithm of u. U is a positive number, so we can define it's a positive function. Then with that, we define f to be this. Okay, u is also smooth. From here, if u is solution of heat equation, if u is solution of this, then you can show that this guy you have here also satisfy. Okay, let me write this way. If u is a solution of heat equation, f will satisfy the equation of that lemma. Can do that. So if f is log u and u is a solution of heat equation, then f will satisfy the equation of that that lemma, the assumption of that lemma. So which apply this. I want us to note that. Then again, let us also note f equals to log u, and this implies this. Let us also note this. Yeah. The Harnack inequality, the Harnack quantity of that lemma is this. Okay, that's the Harnack quantity there. So here we can see this imply f over t is t squared minus partial t of f. Okay, if you have this and f is log u, what does this one tell us? We can say that if f is log u, gradient of f is just gradient of u over u. And the gradient of f squared is just a gradient of u, value of that square, u square. The same thing with a derivative. Okay, so which means this one here implies that f over t is gradient of u square over u minus ut over u. So that's what you have there. Okay, and what we wanted to prove that we have on the board, this quantity that we wanted to prove from Li-Yau, which is ut over u minus gradient of u square over u square plus n over 2t is greater or equal to 0. Okay, this is Li-Yau. This just implies if f over t is defined as this just implies saying f is less or equals to n over 2. That is what this implies. Okay, that is what it implies. And by that, we reduce the theorem of that Li-Yau to just if we can prove that f is less or equal to n over 2. Okay, if you just put there, if f, this is f. Okay, and this is Li-Yau greater or equal to 0. Then you have this. So if you can just, what this theorem is reduced to is proving that f is less or equal to minus over 2. And we now want to use the equation derived from this lemma. Okay, and you know this is the parabolic equation. Okay, E-type equation. We already developed a maximum principle for that, so we can apply maximum principle to show this type of things. So to prove that, what we just do, I will write what I have on the board there, that equation. I write it this way. is greater or equals to minus 2 then don't forget, let's look at the theorem of Li-Yau. The theorem gives us non-negativity condition on the Ricci curvature, which means it's greater or equal to 0. But in the lemma, we have a general one that says is greater or equal to minus k. So to have that, we can just set k to be 0 because k is greater or equal to 0. So if you set k equal to 0, you have that condition which is greater or equal to 0. So to apply this theorem now, we set k to be 0. Then this middle term here, the term with k vanishes. So we have minus, okay. In fact, I will change it to, I will write it this way, plus 2 over nt f into f minus n over 2. So that is that lemma is written that way. So to prove the theorem, we just claim that f minus n over 2, okay, is less or equal to 0. So that is what we wanted to prove here. So we claim this. And if we can establish this claim, then we are done. And how do we establish that claim? We can prove by contradiction. Okay? Proof by contradiction. And then if by contradiction, it's okay, there must be some point. If this claim is not true, if this claim were not to be true, there will be some points where this f is greater than n over 2, and n greater than 2 over 2 is greater than 0. That will be point. Call that point x naught at t naught. And then because m is compact, then if our m is compact, there must be a time when this f reaches its maximum. Okay? So at maximum point, what happens? We cannot apply maximum principle. We know that at the maximum point using maximum principle or second derivative test, as we explained the other time, we know that the gradient of f, so if x naught, t naught, the maximum point, here we know gradient of f at this point, x naught, t naught, will be 0. Then we know that this Laplacian, that is second order derivative of that, will be less or equal to 0. And we also know that partial derivative of f at the point x naught, t naught, that's the point where the f function f reaches its maximum, is greater or equal to 0. So if you have this, it's just like the way maximum principle was proved yesterday. We can just combine that together with this equation here. And with that, if it's 0, this is less than 0, and this one is greater than 0. From here, we see that 0 is greater or equals to minus c of this of f. Okay. Well, at point x naught, t naught. So that's what we have. So at maximum points, this is what you have. And okay, maybe I should just add this here so that it will be clear. You have this. Having this, based on this, it should be greater than this, greater or equals to this. At the maximum point, gradient of this will be 0. So this term is 0. Okay, so which is greater than 2 over nt f x naught t naught minus n over 2. Okay. With this, we claim that this is greater than 0. So, meaning that this one should be greater than 0. And that is a contradiction. That's a contradiction. So this is a contradiction. Meaning that this guy cannot hold. Therefore, we have this. And therefore, the graded estimate is satisfied, is proved. Okay? So that's a way to prove that. And once you have that, we can now prove the Harnack inequality. Okay, the classical Harnack inequality from that graded estimate. So this is the classical Harnack inequality. Let's say time. If you have time, let's quickly look at that. I don't really have that time. So we can move, we can just leave that. That's the normal integration by parts. I mean, normal integration, and we apply some little inequality. Then we'll have this. Okay, so let's move on. So we have discussed it. Now, another example I want us to see before we leave this is an observation which will help us. If you look at equation of scalar curvature under Ricci flow, yes, we used it in yesterday's lecture, in our last lecture. We saw how scalar curvature, okay, let me just say Harnack inequality now. It's an example now because we're going to discuss this Harnack inequality. Maybe let me say for two-dimensional 2D Ricci flow. Okay, so we in a two-dimensional manifold, we know that a Ricci curvature is just 1/2. Okay, R multiplied by G, scalar curvature multiplied by this. This is how Ricci curvature is expressed, where R is a scalar curvature. Okay, and we also know that under Ricci flow, this scalar curvature R evolved this way. Remember? This way. So meaning that under on a compact surface, then the evolution of R under Ricci flow will be so instead of this, you have plus R squared. So this is a semi-linear heat equation. For R. Okay, so this is an observation. And then we observe that instead of U, we have R. If in that equation we substitute U in the Li-Yau graded estimates, we substitute R in place of U. We have, what are we going to have? We have RT. Okay, maybe let me write it this way so that it can look nice. Did the T, okay? That is that is what you have there. Gradient of R squared over R, then plus N/2 T multiplied by R, greater than or equal to 0. But don't forget that in dimension 2, N is 2. So 2 will cancel 2. So I will just have R over T. So this, can we show that this graded estimate holds on compact surface? under the Ricci flow. But this was proved by Hamilton. It was proved by Hamilton, and it is true. You just have to do some modification on what you have here. Do some modification on what we did before, and you define, you do that, then you will be able to prove it. You'll be able to prove this. So that is what we have on the board here. This is a Li-Yau Harnack inequality for two-dimensional Ricci flow. So you have this for point X, and you can show the classical Harnack inequality satisfying this R at point x2, t2, x1, t1. So you have this. Yes, it's not difficult to prove, but we can just move on. What you just need to do, if you can define log R, just like you have log U the other time. Define a function also that will be log R. Then it will come out just the way we prove that, except, you know, in this case n is 2, and some other thing that will come to play, and it's going to be very easy just to manipulate. And you have that. Okay. This is another observation. The result of Li-Yau that we just proved, the graded estimate, which is still on the board. You read here that we prove. Yes. If you have any vector field on the manifold, on compact Riemannian manifold, you can write it. You can write that as this. Exactly. Okay. In fact, if you take an optimal vector field, you substitute in place of x, you will get this Li-Yau Harnack inequality. Let's quickly show that. If you have an optimal x equals to minus gradient of u over u, if we substitute there, we'll get Li-Yau graded estimate back. So this observation helps to say, okay, if you have this, and you have this vector field, if it's a time-dependent vector field under the Ricci flow, then we should be able to get estimate of maybe scalar curvature. Once we have established that, okay, scalar curvature under the 2D, which is very easy to see, satisfy this, then how will a scalar curvature evolve under maybe higher dimension, or maybe dimension 3 to start with, or higher dimension, so that we can have this type of Harnack inequality. This Harnack inequality is going to help us to do to put the control, okay, just like we use some derivative estimate to get control on the covariant derivatives of a curvature tensor. So this one also helps us, because these are bands telling us that, okay, you can compare results at 2 different times. Then we can just move on. In fact, another result we are going to see now is a matrix Harnack estimate, which is called Hamilton Harnack estimate, which is an improvement on this, because this Li-Yau Harnack inequality can compare results at 2 different times, but 2 different times. The Hamilton Harnack estimate compare results, okay, 2 different results at the same time. Okay, that's what we have here. Okay, I said to prove Hamilton matrix function of the Li-Yau result, we need the function of maximum principle for system of equation. Okay, we have a function of this maximum principle in our last lecture. Okay, the one built for tensor. So this is for matrix now. It's for matrices, MIGS matrices. Okay, and our tensor, like a Ricci curvature tensor and metric tensor, is also they're also matrices, so it works the same way, and it was built in the same paper where where maximum principle for tensor was also built. So it's follow the same fashion. Okay, and this is the statement. This is the statement of the theorem. Let them be a closed Riemannian manifold. Okay, I told you anytime I say closed, we still mean compact without boundary. And then now we just reduce that without boundary because we want to deal with Ricci flow. And the Ricci flow that we have been constrained before, we consider Ricci flow on manifold without boundary. Okay, so now if you have this condition, suppose M is Ricci parallel and the M has weakly positive sectional curvature. By Ricci parallel, we have a gradient of Ricci curvature equal to 0. And weakly positive sectional curvature is that you have this full Riemannian curvature, okay, written in local coordinate is greater or equal to 0. For X, Y, they are smooth vector. It's okay. So a smooth vector fit. Then this holds. Okay. Hij is defined as this hold. Okay. Tracing this. If you do trace of this, you will get Li-Yau result back. You will trace this, you get Li-Yau. Okay. That's it. Do the tracing of this is Asian. You do the tracing here, it becomes Laplacian. Let me quickly do that so that we can just if you do the tracing of that result, this result is minus okay. If you do the tracing, you trace Asian, it becomes Laplacian of U. You do the tracing of this, you have of U square over U. So we see this side, okay. Let's use this side. That side is not feasible. So you do the tracing of that. So you have Laplacian of U. Okay. U minus the tracing of G. Okay. We are using metric. You know, this is a tracing. We are using metric G, inverse metric Gij to trace. So the tracing of Gij on this Gij is N. So there you have N over 2TU greater or equal to 0. And this easily implies, okay, U in this case satisfy its equation. So if U satisfy its equation, U is this. So you can substitute here, you have UT divided by U because of U that we have here, that is UT over U minus, okay, square is here, greater of U square over U minus N over 2T greater or equal to 0. So that's why it's called matrix trace. So it's the same as that. Okay, that's the one we discussed. So we need to move, and the proof is long, but a way to do that is just 1 year. So because you have U greater of U, Asian of U, they are bounded function. Okay, they are all bounded. Then the inequality Hij obviously hold for T small enough. So if we can show that Hij satisfy E-type equation of the form, okay, of the form here, you can show that Hij satisfy this, we can prove that Hij just like we have Mij greater or equal to 0. Okay, so you can do that, and with this quantity greater or equal to 0, we can prove maximum principle for symmetric matrices. And the way to do that is this. You define Lij to be this, okay? And that Lij is Hij minus, Hij is already what we wanted to prove, greater or equal to 0, is you take away this U over 2G from it, you define it as L. You can do computation, long computation, okay? You have this, okay? Which is easy to see that this as follows. Then, with that, Hij will satisfy this equation, okay, which is of form 4 that I want to show, that I want to prove. And you have this with all what you have here, phi of Hij greater or equal to 0, just like that maximum principle. You can now apply maximum principle to show that Hij greater or equal to 0. And that one proves this. Hij greater or equal to 0. We have, by application of this maximum principle. If you have this maximum principle with phi greater or equal to 0, then Mij will also be greater or equal to 0 for all time. So that is what you have there. And that is the proof. Okay. So let's check time. Okay. Let's quickly make the following remark. Li-Yau result allow comparison between different points at different times, while the Hamilton matrix result allow comparison between different points at the same time. Okay. Then the matrix Harnack estimates, just like Li-Yau Harnack estimate becomes an equality for the each kernel. If you have each kernel, I showed that Li-Yau becomes equality. I mentioned that. I think we tried to show that. Okay, this is this kernel. I wrote it the other time. And on the Li-Yau it becomes. So also, in fact, we have seen the equivalence between Hamilton Harnack inequality. Okay. Anyway, it is called Li-Yau Hamilton inequality, Harnack inequality. So where this one is just Li-Yau Harnack inequality. So this is Harnack. Li-Yau Hamilton inequality, Li-Yau inequality. So there's equivalence between two of them. So on each kernel, if you are on Rn, if you are on Rn, Euclidean, and you have your each, okay, each kernel. So all these become equality, these become equality in the case. So, and the quadratic function of Hamilton Hamilton matrix Harnack inequality also gives this, okay, with any vector field X. So that's it's a corollary from that. Good. This is the integrated fashion. The same way that is proved, but I just move. So if I'm satisfied the theorem, and you have this curve, which is now a geodesic because our manifold is a geodesic now. It's a geodesic manifold parameterized by Harnack length. Then you have a point S0, which can be taken plus or minus S0 from this I. We can show this. Okay. So gamma of 0 is for a point, and the gamma of S0 for a point in the manifold. This gamma of S is a curve which defines geodesic on the manifold. Okay. Okay, good. So we want to move and discuss Harnack inequality for Ricci flow. Okay, the one we gave for two-dimensional flow is just an example, but for the higher dimension is a bit tricky. Cannot just work the way I showed for the two-dimensional, where we just say, okay, we have semi-linear equation, and then you just put, because here, if you have Ricci curvature, Ricci tensor, the minor tensor, they evolve. Yes, their non-linearity is more subtle than this just R squared that we have here. It's more subtle, so it makes it's not so simple, just like you have the evolution of the scalar curvature. So we say, yeah, Hamilton discovered a highly non-trivial matrix version of Li-Yau type inequality for the Ricci flow on complete manifold with positive Ricci curvature operator. This inequality is called Li-Yau Hamilton inequality, and the theorem is this. Okay, let M, okay, be GT be a complete solution to the Ricci flow on the closed manifold with a weakly positive curvature operator. Then for t greater than or equal to 0, we have this. We have this. And okay, just like Li-Yau, we can prove classical Harnack inequality. And that is just it. So D here is metric dependent now, and the metric is time dependent. So that's why the T here. So this geodesic distance that we mentioned earlier on. So this is now telling us that the curvature, okay, you have a band, can be banded. That's the meaning. And we said it that, okay, one of a way to see that you have your Ricci flow and you deal with singularities that you band curvature. So in this case, show that curvature can be banded. Okay, you can band it with this lower data. Okay, so that is exactly what this result is saying. Okay, so with this, we can now move on and study Perelman function now. Because let's just have a minute break. Okay. Now let's consider Perelman functionals for Ricci flow. Okay. In fact, the story about Ricci flow, if you see all what we have been discussing before, if you look at the story of Ricci flow is about now. All stories started in 1982. Okay, this is 2000. That's about 4 decades now. Okay, so what we have been discussing before is should be in the first 2 decades of Ricci flow. Okay, up to 2002 or there before Perelman's results. So that is the story we have been discussing. Now we want to talk about what happened since the work of Perelman. The first, he has 3 papers which provided the solution of Poincare conjecture. Okay, so the first, titled entropy functional for Ricci flow and their geometric application. So he introduced 2 functional. Before that time, we want to say, okay, can Ricci flow be made a gradient flow, just like a heat equation, so that we can gain some control on certain energy functional, and we'll be able to say, okay, asymptotically, this is the behavior of Ricci flow. But it was not easy to say Ricci flow was a gradient flow of certain energy until the paper of that Perelman, where he actually proved that Ricci flow is a gradient flow. It's a gradient flow, and we'll mention that now. So he introduced some energy functionals. So we want to discuss 2 of them. We call this one F energy functional, and the other one I call it W functional. Okay, 2 of them are defined on the space of a smooth Riemannian matrix. Okay, so well, we will try to, in this paper, I computed the variations of this flow and show that the corresponding gradient flow is a modified Ricci flow. And these functionals are monotonic in time under the Ricci flow. So monotonic quantities are very important tool for understanding Ricci flow. They particularly characterize Ricci flow for which they are constant in time. Okay. So when we consider the space of Riemannian matrix modulo diffeomorphism, okay, we will see mention that because the modified Ricci flow that Perelman has is he has to do a kind of a modulo of the diffeomorphism in the variance of Ricci flow before he was able to get Ricci flow as a gradient flow of that energy function now. So if you now modulo out the diffeomorphism and that scaling, the fixed point of Ricci flow dynamical system now corresponds to what we call steady shrinking or expanding Ricci soliton, while the Ricci brothers correspond to the periodic orbits. And in the study of here, we do not want to have Ricci brothers, so that's a way to show anything that, in fact, the theorems, the monotonicity of this function now allow us to establish that there is no brother other than trivial brothers. So these brothers are periodic solutions. We do not want to have periodic solutions, and we can rule them out in the solution of Ricci flow. Okay. Okay, let's give this definition. Yeah, this is what we call brother. Okay. So this, you know, if you look at this now, look like the way we define solidon. But now you are having scaling constant here, and you are having time-dependent diffeomorphism. So you are scaling the pullback of this metric of T1 and this T2. So this quantity defines what a brother is. Any solution G of T2 now that can be written as this, where G of this T1, I mean T is a Ricci flow. So this is called a brother. Okay. So let me say that again. So a metric GT, if it's soft Ricci flow, it will be called brother in this for some T1 and T2 such that you have G of T2 equals to alpha, which is a scale factor, and the phi T star, which is the pullback of this metric GT1. Okay. And if you can take this alpha as a constant now, for alpha greater than 1, less than 1, equals to 1, will correspond to shrinking, steady, and expanding brothers. Okay. And the example of that will be, okay, obviously shrinking, steady, and expanding Ricci solitons, they are trivial brothers. These are trivial brothers. Okay. So these are what you have. Anything other than shrinking, steady, expanding, you don't have any brothers in Ricci flow. So that's what is called non-existence of trivial brother, or you call existence of non-trivial brothers for Ricci flow. So this monotonicity of the functional that we want to talk about help us to do this, to rule this out. Okay. Now this is the F functional defined by Perelman. So we consider M, which is n-dimensional compact Riemannian manifold. Then F functional is defined as this. This M slant is the space of metric spaces. It's the space of Riemannian metric spaces. So you have the Riemannian metric space composed with a smooth function. So this F comes from here to have, and is defined as this functional. Okay. And if you get this, this is the energy functional that produces gradient flow, which we call the Ricci flow in this case. And maybe we to put our what we are discussing in the perspective, let's use each equation. Okay, let's clean the board and use each equation so that we understand. Okay, now let's say we have each equation. consider its equation. Consider its equation like this on a compact manifold, okay, M, on a compact manifold M, with T, our T now between 0 and this. So we have this. Then it can be this equation can be interpreted as gradient flow of Dirichlet energy functional. It can be interpreted as a gradient estimate of this. I mean, gradient flow of Dirichlet energy functional. We know this. This is the volume measure of manifold. Okay. And what does this mean? Let's quickly show. If you have this and you want to have variation of this energy, okay, if you have variation of this energy, let's say with respect to T of this energy functional, this gives us, you have to differentiate this. Okay, let's add half here, make that energy. So you have to differentiate this, which will give you gradient of U, gradient of UT with respect to the V. And if you apply integration by parts, we are on a compact manifold, so the boundary is not coming in. So apply integration by parts. So you have minus M UT Laplacian of U dV. That is application of integration by parts. Okay. So this says, what this says, if you compare this one with inner products, okay, with respect to this V, let's say we define inner products, U, W, this way, U, W, dV. This is an inner product. So this one can be written as just this inner product minus outside. This is UT part of U. And the meaning of this, okay, is that U equals to T, I mean, UT equals to Laplace of U is the gradient flow. Is the gradient flow of this energy. Okay, so, and this allows us to do a lot of things with this equation, telling us that at some point, okay, before that, let's do a kind of monotonicity, another important thing here. If U now is a solution, suppose if U now solves the heat equation, what does this imply? You can see if U now solve the heat equation, that means UT is Laplacian of U. Then this energy will give you right? This is a positive quantity. This is minus, less or equals to 2. I mean, less or equals to 0. This is a monotonicity. So showing that this energy functional is monotonic. Okay. So we have seen that we can build the heat equation as the gradient flow of this energy. And at the same time, if we say heat flow of this energy is monotonic. The meaning of this is that the solution of heat equation should effectually converge, okay, is to a stationary point. Because if this is less or equal to 0, at a stationary point, it means this guy is equal to 0 at stationary point. The heat dt equals to 0. And if this is equal to 0, it means you have Laplacian of U equals to 0. And the meaning of that is that U is harmonic. That's harmonic function. So what we are saying now that is that effectually, okay, maybe as time goes, then the solution of each equation converges to stationary point, the stationary point of this energy function now, and that stationary point is the harmonic function. Okay, so in this case of Ricci flow. If we can establish this as well, we can show that Ricci flow is a gradient flow of energy functional. Then we can see, okay, it must converge to certain stationary points, okay, when it's equal to 0. And the stationary point in this case should be as time, as we have seen in the original solution that we prove with as time. Here we put as time, Ricci is equals to multiples, lambda multiple of G. And we were able to show that when lambda is less than 0, greater than 0, or equal to 0, we have shrinking, expanding, and steady soliton. Okay, so because of time. And in this case of Ricci flow, what comes to mind is that, okay, if the other time we said, can we just put R in place of U? Oh, and we now say, okay, let's consider a function now in this form. Okay, let's consider function now of this form. If you do it this way, in fact, what you have here, if you can use federation of G, let's say federation of G to be Hij, the way we did the other time, the federation of this Eg, if you solve that, it will give you something of this nature, because we know federation of R, okay, what we did under yesterday, arbitrary federation under Ricci flow. We have federation of R. I think we have something like this with the trace of if G is varied this way, federation of R is minus Laplacian federation of G plus this square federation of H minus Ricci federation of H. And then we also have federation of volume, okay, which is half trace of H with the V. I think this is what we have. So if you use that here, you do federation of this, then you have to do federation of this, like a product here. What we have is something like this, minus Hij Rij minus 1/2 Rgij dV. This is what we have, which is like saying that Hij is, maybe let's use 2 of minus 2 Rij minus 1/2 Rgij. So this is the federation of let's say we want to say the G, the T, and I'm now saying it is minus 2 R this. Okay, don't let me add. Okay, let's leave this one here. Let's leave this one here. Let's just say minus Rij minus 1/2 Rgij. So this one this is the gradient flow of this, but this what you have here is not Ricci flow. In fact, this flow you have here is not even parabolic, and the behavior is not the same as what we expected. So which means this cannot be the energy functional. And the appropriate energy functional is what is given here, okay? And the variation, so this one has this property, is diffeomorphism. Other diffeomorphism is invariant, okay? You have diffeomorphism here. So on G, on F, it is invariant. Then if you have two constants, alpha greater than 0 and any constant beta, if you scale the metric and you scale the function f as well, this is what you have. So f is not scaling invariant, but for the diffeomorphism is invariant, okay? And now with this function now, we can find the first variation of this, just like we did to the evolution of the geometric quantity under Ricci flow. So you can find variance, and that is what you have here. If the variation of Gij is given as Vij, variation of F is given as H, then the first variation of this energy function now is given as this equation 9. We can solve that. Yeah, it's a long calculation with tensor, integration by parts. So we can do that. So, and we have this equation. Okay. So because of let's check time. Okay, because of time, we will not do that. So in this case, this V that we have here, okay, is just the metric trace of Vij. Vij here is a 0-2 tensor. Okay, so that it will look like if you find the time derivative of G, then you can have the Vig now in form of a Ricci tensor. So you can just substitute this one with -2 Rij. Okay, just like we did in the last lecture. So V here is the trace, metric trace of Vij, and this is the first variation of Ricci flow. And it's very easy if we can compute that, though it may be a long computation, but something we can compute. So this is the phi f of G. F is given as this. So there's something that I didn't really mention here. What we did there, the reason why this is coming me, it has a reason. Instead of F, we have to introduce this type of a volume. It's called weighted volume. Okay. So this is a Perelman F energy. So if you want to find variation of this now, you already know variation of G, which is given as Vij, and you know variation of F given as H. So you can find variation of F. So that is a integral M. Variation of this, keep this constant. You know, this one F is a function, okay, which depends on X and T as well. So you have to find the variation of that as well. Here, you know the variation of volume. When you substitute all those, and we have some terms, we apply integration by parts, and we simplify. This is what we're going to have. Okay. So now we still want to, from here, it look like, yes, we can get something that look like a gradient flow. Look at the first term here. So Vij now, we can say Vij equals to this, maybe 2 of this. That will give us a gradient flow. Vij equals, let's say, 2 of what we have there, Rij plus we have this. So where this is the variation of G, which I can just call the G. Let's call it time now. So this one look like a Ricci flow. You have the Ricci flow part. Only this that is left is like a -2 Rij minus 2. Okay, this is the part. So this now can be called gradient flow. Exactly. And this is not exactly Ricci flow, but it has been modified with this guy. This guy exactly is the definition of a Lie derivative. Lie derivative, you know, with the Lie derivative of this vector, if this vector field is a gradient of f, if it's a gradient of f, Lie derivative in this direction is a 2 gradient of f. That is a 2 Asian of f. Okay, so which means you are having a modified Ricci flow with a Lie derivative. And we know that Lie derivative, okay, if this vector that we have here, vector x, generates diffeomorphism. So this one is just a diffeomorphism, okay, combined with this. And because it's diffeomorphism invariance, we know that this is going to be Ricci flow. Okay, just like the talk Ricci flow. Okay, so that is a degraded flow for this that we have from this equation. But to have that exactly, this term here with the term with this, we must get rid of it. Okay, so this is not, it's not automatic that this is graded flow. We have to get rid of this second term here so that it remains only this. And how do we get this term here eliminated? Okay, if you can say v over 2 minus h equals to 0, all this term will be equal to 0. And v minus 2 over h, v over 2 minus h equals to 0 implies that we fix this weighted measure that is fixed. Okay, and we see that here now. So that is what we mean now. So to get Ricci flow as a graded flow of that energy function now, we will eliminate this term. And this can be done by setting v over 2 minus h equal to 0, which amounts to keeping the weighted volume fixed. Okay, so fix this volume and we call it this a fixed dm. We call it a fixed measure on m. We relate f to g by requiring that e minus this e to the power of minus f dv is this fixed measure. Okay, equivalently, we define a section S, which is from M, space of the metric space, the space of the smooth metric to this. We define it by this G and the length of the VDM. This is a kind of a Radon-Nikodym derivative. So the composition of this F and S, we call it F with M, fixed metric. It's a function on M, and we can define it as this. Okay, so we have fixed the volume. Okay, and we have this. In fact, fix the volume to get that. Maybe computationally, it's this is the volume. Okay, we can find derivative of this. Just hold on, so that we see. Okay, we use federation. E minus F dv. Okay, let's do that. What is the federation of E minus F? So we are taking federation of this minus F. Let me write it out so that we can see. This is what we are doing. Federation of this is half trace of h dv. So which means here the trace of h. Oh, sorry. Yeah, in this case now it's not h, it is a vij. The trace of vij is a gij vij. So which is v. All what you have here is v. So this is a v over 2 with the volume. Variation of this one, you differentiate this one, gives you minus variation of f, E minus f. So that we will write it neatly so that you can see well. So this gives variation of D, that is minus variation of F, okay, with E minus F dV. And this one is E minus F variation of dV. So the variation of this is minus H. Variation of F is given as minus H, okay. We have then with this, then variation of this one is what gives us V over 2, and all of this with E minus F dV. Okay. Now, if you fix this, you are saying that it's not evolving. It means variation of a constant is 0. So all this one is 0, which is V over 2 minus H. And because this is what you fix, you have this. It implies that V minus C over 2 minus H is equal to 0. So what we have done is that we have fixed this metric, and that metric that we fix is now what we have as dm. Okay, so that's energy functional, which we have Ricci flow as its gradient is now written like this. Okay, so Ricci flow is now the gradient, is a gradient flow of 2 of this energy functional. So that is what we have. Exactly, these are my explanation. Okay, and then we can show this because F depends on time. If you have this, F also satisfies this with what I've just explained there. You can see that F will be, in this case, let me just show us. This is the M is E minus F dV. Okay, so this implies that you can define F as a ln of dV over dm. So taking partial derivative of F with respect to t, okay, you have this now under Ricci flow. Okay, no, okay, still under arbitrary variation, which you have this. So differentiation of Gij with respect to this, as we have here, okay, is what you substitute here. Tracing Rij gives you R, which is a scalar curvature. Tracing this Isian gives you Laplacian. So this now gives you derivative of F with respect to t is equal to minus 2. Okay, half is in front, so minus 2, we cancel that. That will give you minus R minus Laplacian of F. Okay, so this is saying that, okay, you can have the metric, you know, F is a function on G and F. It couples this. So you have equation that satisfy G as the G dt to be minus 2 Ricci plus, okay, let's take to this local coordinate that we are working, with an I, with a J, F. Then F satisfy this. Okay, this is a backward equation. So you have this. So this is now gradient flow of the Perelman F energy function now. So this energy function now is this equation 10, and then you have 11 here now as the gradient flow. So you have modify it equation with a backward it equation. So this equation is what gives you gradient flow. Why metric is being solved, Ricci flow is being solved forward in time. This it equation will be solved backward in time. Okay, and we can do a kind of time-dependent transformation of this equation 11. So we do that because of this variance in this. If you do this, you get it equation coupled with it equation. That is, you can modulo out, because this modified equation is now involving a kind of a gradient generating diffeomorphism. Okay, so you can now modulo out that diffeomorphism from this equation to get Ricci flow. And a way to do that is that, okay, the first equation here, we are having Lie derivative, okay, of metric in the direction of a gradient of f minus that here. We can add that Lie derivative to it so that we have that. Then we have the Lie derivative in the direction of this. So here, if we take any time-dependent effect of it, you recall that we have a Lie derivative with respect to this xt of g. This is a we know that. Then this of f is if x, okay, let me leave this one. If we define this x as the gradient of some function, that is when you have this. And here you have this as a f square. So if you now add this to here, to modulo out the diffeomorphism invariance here, this is the function of g. Then to here you add Lx of f. Okay, this is time dependent. So what you have left now is a dt minus 2Rij. So this, we cancel this because this guy is this, which is what you have when you minus this plus this. So you have this, which is exactly Ricci flow. And this is minus this plus, because you're having this, which is a so when you modulo out the diffeomorphism variance from here, then you have this. Okay. So we can now find the monotonicity of that energy function now. The monotonicity of that energy function now, just like a monotonicity of the Dirichlet energy that we saw under it equation. We said it is a monotone. And if it's stationary, the stationary points are harmonic function. In this case, this f defined under this it equation coupled with the backward it equation, Ricci flow coupled with backward it equation, that energy function now evolves like this. Okay, which is going to be greater or equal to 0, right? Because this is 2 is positive, this is positive, this is positive, so this is greater or equal to 0. So which means at stationary point, you have the quantity here greater or equal to 0, which is the equation of a steady gradient soliton. This is a steady gradient soliton. You have under stationary, you have Rij plus gradient I, gradient J, F equals to 0. This is an equation of a steady gradient soliton. Just like the way you have harmonic equation under that Dirichlet energy. So that's what this theorem is saying, that you have this monotonicity formula, and by keeping this weighted measure constant, okay? So you have that, keeping this one constant. Moreover, if this is not decreasing in time, and the monotonicity is straight, unless the metric is a steady gradient soliton. Okay, so that's what this is saying. So this is greater or equal to 0. That's monotonicity, non-decreasing monotonicity, or what you call increasing, but now non-decreasing monotonicity in time. And you have equality only when you are on the steady gradient soliton. So, and we can prove that as well, but we'll leave the proof. So this remark, I'll move on. This is a basic example that I want us to quickly look at. Look at this example. Well, if you are on Euclidean space, you can construct this. Take f to be this function. Okay, I just tau here is defined as a t naught minus t. Okay, so EF is e to the minus f now is this. So you can couple this one with the v that will define the weighted measure. So this is the standard each kernel on Rn. So when consider for tau going to 0, going from 0 to t naught. So if you are moving from 0 to t naught, this is now each kernel that we divide the other time on Rn. And one can show that on this, okay, if GF solve 12, that is G solve, okay, G solve the first equation here, and F solve this equation. In fact, we can show that with this example. And with that, you are narrow n, if you take the Ricci coefficient as flat, equal to 0. So Ricci coefficient will not appear because we are on Rn is a flat, Rn is a flat manifold, so to say. Okay, so this energy is equal to n over 2 tau. That is n over 2t minus t. 2t naught minus t. And particularly, this is not decreasing as a function of t in this interval. So that is an example on Rn. So each kernel t on this one still make this optimal. Okay, just like Li-Yau Harnack inequality, Hamilton Harnack inequality on Rn. So, well, let's skip this. So that now, if you look, this one here has been used to rule out steady gradient estimate. Okay, can we rule out expanding gradient estimate? So we can use this energy function now also, but we are going to do a kind of define this infimum of that f to be this. Okay, let's just leave. If you define the infimum to this is just a kind of transformation to say that this lambda, the infimum here, is going to be an eigenvalue of this operator here. So you have this, just like the energy function now, if you get the infimum of that gradient of u naught there, you will see the infimum is going to be an eigenvalue of Laplacian. Okay, so and that is exactly what you have here, where u naught is going to be corresponding eigenfunction. So, and then you can define f naught, you get the value, and so on and so forth. But this is not in interest at this point. So this lambda that we define here, okay, is also monotone. And we can use that to define this monotonicity formula for f. Okay, and with this monotonicity formula, we can prove this. Of course, I said Gij is invariance under this, so under pullback by the homomorphism. Yeah, so lambda of this pullback is also lambda of Gij for any diffeomorphism, and lambda Gij is not decreasing. The monotonicity is straight unless Gij is a steady gradient solidon, and we can say that a steady breader is necessarily a steady gradient solidon. No other breader. Any breader here is a steady gradient solidon. So we have ruled out any other breaders, only the trivial ones, which are gradient solidon. Then, so to do expanding solidon, what you just do is that you have to modify that lambda, that infimum of that energy with this volume. This is V is volume of Gij with 2n. If you do that, you can get this as corollary using the same method there, because you have defined lambda bar in terms of lambda, and this lambda is the infimum of that energy. Use the same. Then you can now see under this place, a steady breader is going to be an expanding breader. So we can now say expanding or steady breaders are on the compact manifold are necessarily as time. So we have this functional has helped us to be able to rule out steady and expanding breaders. So to do that of shrinking breaders, this energy functional is defined. So this one is a modification of F energy, okay? And instead of E minus F, you have E minus F over 4 pi tau n over 2 with these constraints, okay? This constraint equals to 1 here. So where tau of t is a function of t is greater or equal to 0. I mean, it's greater than 0. It's a positive time factor here. And Gij is a Riemannian metric. F is a smooth function on M. So this is a W function now defined this way. And as well, just like what we did under F function now, we can find the first variation as well. In fact, the first variation it will give us this. It is so easy with what we have done. We'll be able to do this. Then from here to, okay, you can say the V, we can define energy functional here. And to do that, we need to get rid of this term, V over 2 minus H minus N sigma over 2 tau, get rid of that. And to get rid of that means that this weighted measure here, we have to fix it. And fixing that imply that this is equal to 0. Use the same, and we see that the V is a gradient flow of this together with F satisfying this factor. So under that, which we now have this as a gradient flow, this modified Ricci flow, this backward heat equation, and the tau dt satisfy -1. Okay, this should be the tau, not the tau dt is -1. So, and when you do the modulo out of the homomorphism, just like I did the other time, this one becomes the Ricci flow, and this one is gradient of F square is added. So you have this system of equation. Ricci flow coupled with backward heat equation is a gradient flow of that W function now. So, and we can also prove this under Ricci flow, under that system. If you consider this system, is system 17, and the W function now, we can prove this under Ricci flow. And this is also monotone, because it's also greater than 0. It's monotone in time, and it's strict, except we are the shrinking gradient solidon. So what you have inside this integrand is equation of a shrinking solidon. You remember from beginning, we have an equation of solidon like this. Okay, and we say if this is equal to 0, that is a steady solidon. That is why you have this. If this is less than 0, you have a shrinking solidon. When it's greater than 0, you have a okay. If this is greater than 0 now, in this case, the way I wrote it here, you have a gradient solidon. And that is why you have there. That's why you have, if it's steady, you will have plus I A F minus 1 over 2 tau Gij. equals to 0. So if it is meaning that this lambda is 1 over 2 tau, okay? So that is good. So you can now use this one to rule out shrinking breadth. And we can quickly give this example too, using the Euclidean, okay? So this is the example. And I have this. You can define the infimum of this as well and see the energy. And we use that for this monotonicity formula that we have here. Okay. So you can have this proposition. Just we have under the F. And we can have this a shrinking gradient soliton lives on this interval from minus infinity to 0 and satisfy this system. So, and this is where we are going to stop for today. So we have come to the end of the lecture. So I want to appreciate you once again for coming. So thank you very much for listening. Most especially, I will appreciate Simpra and people from ICTP for sponsoring this lecture. So I say thank you.